How do electrical transfer functions use characteristic equations? Have you ever wondered how electrical systems respond to different inputs? One key to understanding this is through transfer functions and characteristic equations. Let's break it down. In electrical engineering, a transfer function represents the relationship between the output and input of a linear time-invariant system. This is done in the Laplace transform domain, where the transfer function is typically expressed as a ratio of polynomials. The variable used here is the complex frequency variable, which is often denoted as S. Now, the characteristic equation comes into play. This equation is derived from the denominator of the transfer function, known as the characteristic polynomial. To form the characteristic equation, we set the denominator polynomial equal to 0. The roots of this equation are called poles, and they are essential in determining how the system behaves. So, what do these poles tell us? First, they help us understand stability. If all poles have negative real parts, the system is stable. This means that the system will return to its equilibrium state after a disturbance. Next, poles also influence the transient response of the system. They dictate how the output evolves over time, including aspects like oscillations and damping. This is crucial when designing systems that need to respond predictably to changes. Additionally, the locations of the poles provide information about natural frequencies and damping ratios. These factors describe how the system reacts to inputs, which is vital for engineers to know. The process begins with modeling the electrical circuit using Kirchhoff's laws. This leads to differential equations that describe voltages and currents in the system. Once we have these equations, we can transform them into algebraic equations in the Laplace domain. This results in the transfer function, which is often written as g of s equals b of s divided by delta of s here. B of s is the numerator polynomial, and delta of s is the characteristic polynomial. By solving the characteristic equation delta of s equals 0, engineers can find the poles that reveal the system's dynamic properties. For instance, in a resistor-inductor-capacitor circuit, the roots of the characteristic equation indicate whether the circuit is underdamped, overdamped, or critically damped. This directly affects how the output voltage or current behaves over time. It's also worth noting that zeros, which are the roots of the numerator polynomial b of s, play a role too. They indicate frequencies where the output is blocked or attenuated, adding another layer to the analysis. In practical terms, understanding the characteristic equation allows electrical engineers to predict how circuits will respond to various inputs. This knowledge is essential for designing controllers or compensators that modify system behavior. It also enables engineers to analyze frequency response and stability without needing to solve time-domain differential equations directly. In summary, the characteristic equation derived from the transfer function is a vital tool in control systems and signal processing within electrical engineering. It connects the mathematical model of a circuit to its physical dynamic response, helping engineers create more effective and reliable systems.